Hello everyone, welcome back. In this particular video, we're going to continue with our discussions on ortho-para directing groups. In the previous video, we looked at the nitration of toluene, and we saw that the methyl group in toluene makes toluene an activated aromatic, and toluene undergoes nitration about 25 times faster than benzene. And when we get the products, we see that we make major ortho and para products. And so we call toluene an ortho-para directing group. In this particular video, we're going to look at the nitration of anisole as another example of ortho-para directing effect or as an ortho-para directing group. Now, anisole is methoxybenzene. So this molecule here is anisole. And when we do nitration of anisole, very similar to toluene or any other substituted aromatic compound, a benzene-based aromatic compound, we can expect three possible products. We can get the ortho-nitroanisole, the meta-nitroanisole, or the para-nitroanisole. In fact, we usually get a mixture of these products. Now, in the specific case of the nitration of anisole, the reaction is about 10,000 times faster than benzene, which means that the methoxy group makes anisole highly activated. So the ring is very activated, okay? So that's what we're gathering here. So the methoxy group makes the ring very activated. And the methoxy is a strongly activating group, essentially. So now, how do we understand this? Why is the methoxy group making it strongly activated? Now, as far as the anisole group is concerned, or the anisole molecule is concerned, and the methoxy group is concerned, we can see two factors at play here. The oxygen is more electronegative than the benzene ring. So it can withdraw electron density from the benzene ring. And so this is, we can say that the methoxy group is inductively electron withdrawing, which would mean that it should deactivate the ring towards electrophilic aromatic substitution. So the inductive effect of the electronegative oxygen atom is going to deactivate the ring towards electrophilic aromatic substitution. But there is another effect at play here, which is the resonance effect. So what we can see is for molecules like anisole, where we have a substituent with lone pairs on an atom adjacent to the aromatic ring, or we can say it's the benzylic position essentially. So whenever we have lone pairs here, these lone pairs can be supplied to the aromatic ring through resonance. So we can write several resonance forms here. So a negative charge here, double bond, double bond. Electrons would get pushed. Double bond OCH3 with a formal charge, lone pair over there. Double bond here, and negative charge over here. And then we can do further resonance using that lone pair, which is going to give us double bond OCH3, lone pair, formal positive charge over there. A double bond, and negative charge here. And now this negative charge can be pushed back to the oxygen atom as a lone pair. So we get OCH3, 2 lone pairs, double bond, and double bond. So these are all the resonance forms for anisole. And what we see in these resonance forms is that the resonance enhances the electron density. In fact, I think there's no need for the here. We can just say resonance enhances electron density in the ring. Because what we see is among the various resonance forms, there are at least 1, 2, and 3 resonance forms where there is a negative charge on one of the carbon atoms of the ring. So that is sort of denoting an enhancement of the electron density. That carbon is more electron rich now. And so since it enhances the electron density, that means resonance is activating the ring towards an electrophilic aromatic substitution. And what happens in anisole, so what happens in anisole is that resonance is the dominant effect. Resonance is the dominant effect here. And so because of that, even though the oxygen is electron withdrawing and it is inductively pulling away electron density, the resonance effects adds electron density to the ring and makes it activating. And overall, we can see that this resonance effect is a major effect because the molecule is about 10,000 times more faster in electrophilic aromatic substitution reactions when we compare it to benzene. Next, let's try to understand the product distribution that we see in this particular reaction. Why is ortho and para favored over meta, and why is para formed in a higher amount than the ortho product? To understand this effect, we will have to dig into the mechanism of the reaction, and for the formation of each one of these products, we'll have to look at the mechanism for each of these products. So let's get started. We will start with the ortho product first. Now, since we are doing a nitration reaction here, or we're using the nitration reaction as an example, remember that the electrophile in a nitration reaction is a nitronium ion. So let's start with the formation of the ortho product. So if we start with methoxybenzene, or anisole, as it's commonly called, anisole can react with the nitronium ion. And since we are trying to make the ortho product here, we will have to use the pi bond that's associated with an ortho position. So we can use this pi bond here. And this attack by the pi bond on the nitro group is going to give us a sigma complex. So here we have our sigma complex. Now, as always, the sigma complex is resonance stabilized. So we're going to draw all possible resonance forms for the sigma complex here. So we can push each of these pi bonds one after the other. So there we go. We have a hydrogen here, a nitro group here. The double bond has moved and positive charge has moved. The carbocation has now moved. And then we can draw another resonance form where we have double bond over here now, OCH3, lone pairs, carbocations over there, double bond is here, H and NO2. And At this point, notice that we are not done. There's yet another resonance form that we can draw here, and that would involve a lone pair on that oxygen. Because we have a lone pair next to this carbocation, we can actually use that lone pair in doing resonance. So we're going to get OCH3, one lone pair, formal charge, double bond, H, and NO2. So those would be all the resonance forms for an ortho attack. So for the meta attack, I have to use a pi bond again that's associated with the meta position here. And the pi bond that we used here for showing the ortho attack would work fine because that's also associated with the meta position here. So that pi bond is going to attack the nitronium ion, and it will give us a sigma complex for the meta attack. And now this time I connect the nitronium ion over here. I'm doing that because we're trying to show the mechanism for the formation of the meta nitro product. So the nitro group is connected to that carbon. The positive charge forms at the ortho carbon instead. So the carbocation is generated at the ortho carbon. And now, like the other sigma complex, this sigma complex is also resonance stabilized. So these are all resonance forms for these sigma complexes. So we can draw additional resonance forms. So where we have methoxy, lone pair, double bond comes here, carbocations here, H and NO2. And then we move the pi bond over. OCH3, lone pair, double bond, positive charge, H and NO2. And I think those would be all the resonance forms that we can draw for the meta attack. So we have those. And we can do similar resonance forms for the para attack. So for the para attack, again, we start with the anisole molecule, and the aromatic ring attacks the electrophile, which is the nitronium ion. And this time I have to use this pi bond here because I'm going to attach, or I want to attach the nitro group to the para carbon. So we have to use a pi bond that involves the para carbon here. So the sigma complex that's formed initially is going to be OCH3, lone pair, pi bond here, H and NO2, and there's a carbocation here. And then we can do resonance on this sigma complex, where we can use the pi bonds in the ring. So we have double bond here, OCH3, lone pair, pi bond there, H and NO2. And the carbocation is over here. And now from this particular carbocation, we can draw two possible resonance forms, because what I can do is I can move this pi bond over. That's going to give me one resonance form. Where we have the OCH3, double bond here, double bond, H, NO2, H, carbocation over there. And from the same resonance form, because we have the oxygen with the lone pair next to it, we can draw an additional resonance form where I use the lone pair here. So that's going to give us a different resonance form where we've used the oxygen lone pair. So we have the OCH3 lone pair, positive charge, got double bond, NO2 and H. So what we notice is for this para attack, again, we are able to draw 4 possible resonance forms. Now, as we already know, an additional resonance form means additional stability. Okay, so additional resonance forms implies stability. And so basically what we see in these resonance forms for the formation of the sigma complex is that the sigma complex that leads to the ortho product and the sigma complex that leads to the formation of the para product, they have one additional resonance form compared to the sigma complex that leads to the meta product. And this additional resonance forms makes the pathway leading to these products, the ortho product and the meta product, more favorable, more stable. And hence, those are our favored products. And so the methoxy group here, therefore, is another example of an ortho-para directing group. So the methoxy group is ortho-para directing. Now, the second thing that we want to understand here is, why do we get more para here? And that has to do with a steric concern here. So the sigma complex that's formed here, in case of the ortho attack, this sigma complex has some steric strain associated with it, because you have the methoxy group and you have the nitro group next to each other. So that leads to some steric strain. And that strain is missing in the sigma complex that leads to the formation of the para-nitro product. So sterics explains why the para product is favored or further favored over the ortho product. So an additional resonance form for the sigma complex explains why ortho and para are favored over meta, and steric strain in the ortho sigma complex explains why para is favored over ortho. So this way, we are able to understand the product distribution in the nitration of anisole and understand why the methoxy group is such a good ortho-para directing group. I hope you find this discussion useful. Bye.